Now we go to somewhat different sort of crystallographic activity. Herbert Hauptman, come on.
Minimal principles occur frequently in nature, and we should therefore not be surprised that for the solution of the phase problem in X-ray crystallography, nature would choose to give us still another minimal principle. But first, I think a little background is in order. It was Albert Einstein who once said, in effect, that nature is subtle, but she is not mean. X-ray crystallography is now 76 years old, and the history of the phase problem during this period provides a beautiful example of the correctness of Einstein's view. This period is conveniently divided into two roughly equal halves. At the beginning of the first half, nature set a subtle trap and gave crystallographers the diffraction intensities, but not their phases. The X-ray crystallographies, falling neatly into this trap, believed that without the phases, routine structure determination was not possible. It was argued that the phases of the structure factors, as well as their magnitudes, were needed if one is to calculate the electron density function. Since the values of the phases could presumably be arbitrarily assigned, the phase problem was thought to be unsolvable, even in principle. It was not until about 1950, some 38 years after the famous experiment of Friedrich, Knipping, and von Laue, demonstrating the scattering of X-rays by crystals, that crystallographers finally came to understand that owing to the atomicity property of real crystals and the great redundancy of the available diffraction intensities, the atomic position vectors were not only determined by the experimental data, but were in fact greatly overdetermined. Hence, the values of the phases were also determined, and the missing phase information was therefore to be found in the measured diffraction intensities. When the probabilistic machinery was set in place in the early 1950s, it became clear how the needed phase information could in fact be extracted from the available diffraction intensities. Earlier in this meeting, we have seen how far these methods can be pushed with the solution by Dave Langs of the structure of grammacidin A by direct methods. By exploiting the atomicity property of real crystals and the availability of diffraction intensities to atomic resolution, crystallographers have been obtaining routinely the structures of small molecules for some 35 years. With the advent of macromolecular crystallography, some 35 or so years ago, nature set a second, far more subtle trap for crystallographers by providing diffraction intensities for macromolecular structures, but at less than atomic resolution. And crystallographers again fell into the trap. It was now argued that owing to the limited resolution, the diffraction data were not sufficient by themselves to determine atomic position vectors. Therefore, the phases were once again thought to be not determined, and the phase problem for macromolecular crystallography was thought to be unsolvable, even in principle. Thus, new methods were sought, and additional information provided by the methods of isomorphous replacement and anomalous dispersion served to fill the gap. However, in my lecture today, I hope to provide convincing evidence that this argument, like its predecessor some 38 years earlier, is incorrect, and that the available diffraction intensities at less than atomic resolution are nevertheless sufficient to determine unique values for the phases. The key is provided by the minimal principle, which also suggests a possible scenario, not yet fully developed, however, for actually determining the values of the phases in terms of the measured diffraction intensities alone. As with small molecule crystallography, the method exploits the probabilistic machinery introduced some 38 years ago, but depends also on more recent developments. So I want to describe next precisely what the minimal principle is. This is the minimal principle. We have on the first line a function defined in this way. The important variables in this function are what are called phi sub hk and phi sub lmn. Phi sub hk is, as defined here, a linear combination of three phases. It's a triplet structure invariant. As all of us know, the phases are things which crystals have and which crystallographers would like to get. But the phases are very slippery things because their values depend not only on the crystal structure, but also on the choice of origin. It is therefore necessary to introduce special linear combinations of the phases, the so-called structure invariants, which have the property that their values are uniquely determined by the crystal structure and are independent of the choice of origin. In my lecture today, I will focus on two kinds of structure invariants: the linear combination of three phases, phi h plus phi k plus phi minus h minus k, the so-called triplets, and the linear combinations of four phases, phi sub l plus phi sub m plus phi sub n plus phi minus l minus m minus n. It is for the reason that the structure invariants serve to link observed magnitudes with desired phases that the minimal principle is defined initially in terms of the structure invariants which appear here. This function then, well, I should say that we begin with a set of phases. In order to fix the ideas, we should think in terms of possibly 200 or 300 phases whose values we hope to determine and which, by means of the work that I will describe, I believe can be obtained at one stroke in terms of a rather large number of known magnitudes. So we have here a function of structure invariance. This is a double sum taken over all the three-phase structure invariants which can be constructed from the basis set of phases. Here we have a triple sum taken over all the four-phase structure invariants, phi sub l m n, the so-called quartets. We'll be particularly interested in the so-called negative quartets, which I will explain a little bit later. We have here then a function of structure invariance, a function which is independent of the choice of origin, since the structure invariants themselves are independent of the choice of origin. Also appearing in this function of invariance are, well, we see in the first place that this function is a rather simple kind. It's a weighted sum of squares. From the cosine of phi, we subtract a quantity t sub hk, which we'll see is the expected value of the cosine of invariant phi sub hk. W sub hk and W sub lmn are simply weights which are expressible in terms of known magnitudes. They are defined on this slide. Here, W sub hk is defined as the inverse of the variance of the cosine of the triplet phi of h and k, and it's something which can be calculated in terms of known magnitudes E alone. Similarly with the weight W sub lmn. It's the variance defined here. The quantity T sub hk is simply the expected value of the cosine, also a quantity which can be calculated once the probability distribution of the structure invariant has been derived, and I will describe that probability in just a probability distribution in just a few minutes. In a similar way, T sub Lm and n, the expected value of the cosine of the quartet phi sub L, m, and n is expressible in terms of known magnitudes E alone. So what we have here is a function of structure invariance, and because the structure invariants are themselves expressed in terms of individual phases, we have defined implicitly a function of the individual phases themselves. The minimal principle states very simply that the correct values of the structure invariance are those which minimize this function as a function of structure invariance, subject to the constraints imposed by the identities which the structure invariance must satisfy. Now, I haven't said anything about these identities yet. The identities among the structure invariants come about because with a basis set of phases, say of 200 or 300 phases, it is possible to generate a large number of triplet invariants and a large number of quartet invariants. The number of triplets typically may be an order of magnitude greater than the number of phases, and the number of quartets, negative quartets, may be 3 orders of magnitude or so greater than the number of phases. Since there are so many more structure invariants than there are individual phases, it follows that identities among the structure invariants must hold. And so what we try to do then is or what the minimal principle tells us, is that the correct values of the structure invariants are those which minimize this function of structure invariance, subject to the constraint that the identities among all identities among the structure invariants which must hold do in fact hold. Now, since it's not a very easy thing to find the values of those structure invariants subject to the requirement that all identities among the structure invariants hold, we have another formulation of the minimal principle, which is expected to be a more useful one, and that is simply this. We now imagine that this is a function of individual phases defined implicitly by means of these two relationships. And the minimal principle now states that those phases are correct, which minimize this function as a function of the phases. Now, what I want to do is to describe next, briefly, the nature of the probability distributions of the triplets and the quartets. It has been known for a long time that the conditional probability distribution of the triplet, phi sub hk, which is defined in this way, assuming as known the 3 magnitudes, eh, ek, and eh plus k, is given by this expression. It's a very simple exponential function, and it has a maximum when the structure invariant phi sub hk is equal to 0. I should point out that this is the distribution when we assume all atoms in the structure to be identical, that there are n atoms in the whole unit cell, and I've done it in this way because it simplifies the expressions that we have to deal with, and also because it shows very clearly that with increasing complexity, as n increases, the value of the parameter a on which this distribution depends decreases with increasing complexity of crystal structure. The parameter c is not important. It's merely a normalizing number which serves to normalize the distribution. From this distribution, we can readily show that the most probable value of the invariant is 0, and that the expected value of the invariant, of the cosine invariant, is the ratio of these two Bessel functions, which can therefore be calculated. I should mention here that the expected value of the cosine invariant is always positive because the parameter a sub hk, which is defined in this way, is always positive. So the expected value of the cosine invariant, which on the previous slide appears as t sub hk, is expressible in this way in terms of magnitudes of the normalized magnitudes of the structure factors EH, EK, and EH plus K. On this slide, I've shown the analogous distribution for the quartet. And I put the two slides together in order to stress the similarities between the two probability distributions. The distribution for quartets was found about 15 or so years ago. I'm using here an approximation to that distribution, which is good enough for our present purpose. And we see that this distribution has exactly the same form as the distribution for the triplet, except that the parameter A, which appears here, is now replaced by a different parameter B. And the parameter B is defined in this way. And it depends on not 3 magnitudes, which the parameter A depends upon here, but 7 magnitudes, EL, M, N, EL plus M, plus N, and also these so-called cross terms, EL plus M, EM plus N, and EN plus L, the sum of the squares minus 2. So we see the similarities between these two distributions, and we therefore expect that the average value of the cosine here should be exactly the same as it is here, except that B replaces A, and that turns out to be the case. There is, however, one important difference between this distribution for quartets and this distribution for triplets, and that is that the parameter B, on which this distribution depends, may now be positive or negative, depending upon the value of this expression in braces. If the parameter B is positive, the expected value of the cosine is greater than 0. If the parameter B is negative, the expected value of the cosine is less than 0. And we obtain, in this case, in the case that B is less than 0, and the expected value of the cosine is therefore also less than 0, we obtain in this way the so-called negative quartets. From the present point of view, the existence of the negative quartets is of the greatest importance, which I will explain in just a few minutes. But first, I want to show pictures of these distributions so we can see very clearly what they look like and the resemblances and the differences. This is the distribution of the triplet when the parameter A is 2.3. We see that the distribution has a maximum at 0 when the structure, the most probable value of the structure invariant is therefore 0. But for the negative quartets, when the parameter B is negative, let's say minus 1.2, the distribution looks like this. And the most probable value of the invariant is then 180 degrees. And the expected value of the cosine of the invariant is negative in this case, positive in this case. Since the parameters A here and B here are rather large, the estimates, well, the variance of the distributions are both rather small, and the estimates of the cosines are reliable. However, for a macromolecular structure, the parameters A and B are never very large, and the distributions, therefore, are much flatter than they were in the earlier case. Here, when the parameter A is 7/10, the distribution looks like this. Again, the most probable value is 0, but the estimate, 0 for the structure invariant, is now not a very good estimate because the variance of this distribution is rather large. And the estimate for the cosine of the invariant, which is the expected value of the invariant, is also not very reliable. For the quartet, the situation is even worse. Here is the case that B is minus 7/10. For a macromolecule, A values of the order of several tenths are rather typical, but B values of the order of several hundredths are more typical. In that case, although the most probable value of the quartet is still 180 degrees, the estimate of 180 degrees for the value of that quartet is a very unreliable estimate, and the estimate of the cosine of the quartet, which is the ratio of the Bessel functions which I showed earlier, is also very unreliable. I've spoken about the identities which must exist among the structure invariants. And I would like now to describe in a little more detail what the nature of these identities is. Because it turns out that the identities, as I've already indicated, the identities among the structure invariants play a crucial role in enabling us to understand why the minimal principle is valid. I've already indicated that the structure invariants are determined by the structure alone. However, the structure invariants are not uniquely determined by observed intensities alone, and the reason for this is that there are two structures, two enantiomorph structures, which are permitted, enantiomorphous structures, which are permitted by the observed intensities, so that the observed intensities alone determine only the magnitudes of the structure invariants and not their signs. There are two possible signs for each structure invariant, one corresponding to one enantiomorph and the other corresponding to the other enantiomorph, so that it's only the cosines of the structure invariants which are uniquely determined by observed magnitudes. The signs of the structure invariant depends also on the choice of enantiomorph, and a major headache in structure determination by direct methods, particularly for macromolecules, is how to separate out the two enantiomorphs. If all we can estimate are the cosines, then we have the problem of determining the signs of the structure invariants themselves, which are consistent with a specified enantiomorph. And to this end, the identities which exist among these structure invariants play the crucial role. Here we have the quadruple identity, which is a relationship which must be satisfied among four suitably chosen triple structure invariants, three-phase structure invariants. This is an arbitrary structure invariant. This is another structure invariant, which is obtained from this one by replacing H by minus H, K by L, and minus H minus K in this way. And in this way, as you can see, we have defined four structure invariants in a very special way. Phi sub k and phi sub minus k cancel, and so on. Phi sub L and phi sub minus L cancel, so that by simply adding up these four triplets, we get a relationship among the structure invariants which must of necessity hold. Here is another identity which holds among quartets. It's called the trio identity, the first of two trio identities. Here is an arbitrary quartet. Here's another quartet obtained from this by replacing L by minus L, M by minus M, N by P, and so on. And this is a third quartet defined in this way. Again, just as with the quadruple relationship shown on the previous slide, the sum of these three quartets must be identically zero, because again we have, on account of Friedel's law, that phi L cancels with phi minus L, phi M with phi minus M, and so on. So here we have another identity which, as I'll describe in just a few moments, is of critical importance in separating out the enantiomorphs. And finally, there's another, I'm on the wrong side. Well, I'll leave that there. If we concentrate on the left-hand side, we have the second trio identity, which is formed by two triplets, phi h plus phi k plus phi minus h minus k, and this one, and a quartet. Two triplets and a quartet also satisfy an identity of this kind, and for exactly the same reason as I showed on the previous two slides, the cancellation of phi h with phi minus h, phi k with phi minus k, and so on. So here we have another trio relationship, an identity among structure invariants which must of necessity be fulfilled. Now I want to describe how the how the identities among the structure invariants serve to separate out the enantiomorphs. I'm assuming first that and I've called this enantiomorph discrimination using the quadruple identity. That means we have 4 triplets whose sum is of necessity identically 0, as I've shown on an earlier slide. I'm making the assumption now that we obtain initial estimates not of the triplets themselves, but of their cosines. And the assumption which is made is that, and I'm using the expected value of the cosine to make the estimate. And of course, this estimate is not a very good one, especially if the distribution has a large variance. But we'll assume anyhow that we make an initial estimate of the cosine by using its expected value. That means there are, and I'm assuming also for simplicity, that the estimates are such that each of these structure invariants, each of these triplets, is estimated to be plus or minus 30 degrees. I should stress once again, there's an ambiguity in sign because each triplet has 2 possible values depending on the enantiomorph, one with the plus sign for one enantiomorph and with the minus sign for the other. And I'm making the simplifying assumption here, although it's not necessary to do this, that all estimates are plus or minus 30 degrees. Well, let's fix the enantiomorph by specifying arbitrarily the sign of the first triplet. Let's make it plus 30 degrees. The enantiomorph is then fixed. In how many ways now can the quadruple identity be fulfilled? Remember, the quadruple identity is this. The sum of the 4 triplets must be 0. Well, we see that there are 3 possible ways of satisfying this identity. One in which T sub 1 is plus 30, T sub 2 is plus 30, T sub 3 is minus 30, and T sub 4 is minus 30. In that case, the sum of these 4 triplets does in fact satisfy the quadruple identity. But there are other ways of doing it. We can choose T2 to be minus 30, T3 to be plus 30, and T4 to be minus 30. Again, the quadruple identity is satisfied. And finally, there's still another combination of signs for which this identity is satisfied. And so if we want to use the quadruple identity to fix the enantiomorph, that is to say, to determine the signs of all the triplets consistent with the sign of the very first one, we see that the quadruple identity is not a very good way to do it, because there are many ways of combining different signs for the remaining 3 triplets. So the quadruple identity alone is a poor way to attempt to fix the enantiomorph. And of course, we get an additional complication because of the fact that in general, the triplets will not all be estimated to be plus or minus 30 degrees. Some might be plus or minus 20 degrees, others plus or minus 40 or 50 degrees. And then we have the additional problem of adjusting, of determining not only the correct signs for the triplets, but also of adjusting their values so as to force this identity to hold. So in fixing the enantiomorph, we have a double problem. We have to fix a consistent set of signs to the structure invariants, consistent with a specified enantiomorph, and then we have to adjust their values in some sort of a least square sense so that this identity is exactly fulfilled. The triplets then are seen to be a very poor way to resolve this problem of enantiomorph specification. But let's see what happens with the negative quartets. I'm assuming that Q1, Q2, and Q3 now are negative quartets which satisfy the first of the trio identities. The sum of the 3 quartets is equal to 0. Since the quartets are negative quartets, their estimates lie between 90 degrees and 180 degrees, in contrast to the case of the triplets, where the estimates of the triplets must always lie between 0 and 90, because the cosines of the triplets are, the expected values of the cosines are always positive. For negative quartets, though, the expected values of the cosines are always negative, which means that the quartets themselves must lie between 90 degrees and 180 degrees, or between minus 90 degrees and minus 180 degrees. Well, I'll assume, as I did on the previous slide, that we have initial estimates equal to plus or minus 120 degrees, the cosines of 120 degrees being negative, which is, of course, consistent with the fact that these are assumed to be negative quartets. And I'll assume for simplicity that all values are plus or minus 120 degrees. We now fix the enantiomorph by choosing the plus sign for the first quartet. Q1 is plus 120 degrees. Now, in how many ways can we satisfy the trio identity? Now it's plain to see that there's only one combination of signs for Q2 and Q3 for which this identity will be satisfied. That combination of signs being that Q2 and Q3 must also both be equal to 120 degrees, because only in this case will the sum of the three quartets add up to 0 or 360 degrees. In other words, the signs of the remaining two quartets are fixed by the specified sign for the first quartet, Q1. In short, once the enantiomorph is fixed by choosing the sign plus for the negative quartet, Q1, the signs of Q2 and Q3 are of necessity also positive. Now that, of course, greatly facilitates the problem of enantiomorph specification, because now we see that it's a much easier thing using negative quartets to assign signs for all the quartets which are consistent with a specified enantiomorph. Of course, we still have the problem that in general, the quartets, even with the signs correctly chosen, will not satisfy this identity exactly. If we take as the initial estimates of the cosines of the quartets their expected values, in general, we'll get values different from plus or minus 120. We might get plus or minus 100 or plus or minus 140, numbers like that. And so with those numbers, no matter, even if we choose the signs correctly, we still won't satisfy this quartet exactly, so that again, a least squares adjustment to the initial estimates of the quartets is called for in order that this identity, that all such identities, in fact, be satisfied exactly. And finally, I'll say a few words about the second trio identity, which uses two triplets and a quartet, and which satisfy this identity. The sum of the two triplets plus the negative quartet must be identically 0 if these structure invariants are suitably chosen. Again, we're assuming that the estimates of the triplets are in the range of 0 to 90 degrees or 0 to minus 90 degrees, and we'll assume that the expected values of their cosines turn out to be such that the values of these two triplets are initially estimated to be plus or minus 50 degrees. And 50 degrees lies between minus 90 and plus 90. The quartet, being a negative quartet, must have a value between 90 and 180, or between minus 90 and minus 180. And we'll assume that the expected value of the cosine is such that the initial estimate of the negative quartet is plus or minus 100 degrees. Well, let's fix the enantiomorph by choosing the plus sign for the negative quartet. Now again, just as shown on the previous slide, this trio identity, consisting of two triplets and a quartet, can be satisfied in only one way. If Q3 is chosen to be plus 100, T1 and T2 must both be minus 50. Otherwise, the identity here will not be satisfied. Now, in this case, of course, I've purposely chosen numbers such that with the initial estimates, the identity is exactly fulfilled if the signs are chosen properly. But again, in general, the initial estimates will be such that this identity will only be approximately satisfied with the correct combination of signs. And what is then called for, once again, is a least squares kind of adjustment to the initial estimates of the three structure invariants, which together with the correct combination of signs will lead to new values of the triplets and the quartets for which this identity is then exactly satisfied. We must remember that in all cases, the identities must be satisfied. However the phases are chosen, they must be chosen in such a way that these identities must be satisfied. And that remark lies at the basis of this whole idea. Now I've written down once again what the minimal principle is, and I'm writing it down in two ways. Again, I've simply repeated the equation which I showed on the first slide, and now we can see, in view of the discussion which I've just given, why the minimal principle is at least a plausible one. Incidentally, I'm not going to prove in a rigorous way the minimal principle here, because this is not an appropriate forum for that. What I hope to do is simply to make plausible the idea behind the minimal principle. For the structure invariance, the minimal principle simply says that we seek that those values of the structure invariance for the triplets and the negative quartets are the correct values for which this function of the invariance is a minimum subject to the condition that all identities which of necessity must hold among the structure invariants do in fact hold. Now, as I've already indicated, even with a basis set of phases consisting of some 200 or 300, there are there are several 100,000, okay, 5 more minutes? 5 more minutes?
You'd have 5 minutes.
And then another 5?
No.
No? Oh, sorry. Well, I'll quickly go through.
5 minutes and then 5 minutes.
And then 5 more. Okay, okay. Well, what the minimal principle is now saying is that we want to choose for the values of the structure invariance those values which minimize the difference between the true value of the cosine of the invariance and the expected value, subject to the condition that all identities which must of necessity hold among the structure invariants do in fact hold. And that's why we have a sum of squares of residuals here. We're trying we are not prepared to accept as the true value of any cosine invariant its expected value. We're not trying to do that. All we're saying is we want the true cosines of the invariants to differ from their expected values in the smallest possible way, subject to satisfying the identities which must hold among the structure invariants. Now, the requirement that identities hold among the structure invariants is a very stringent one, because if we have only 200 or 300 phases in the basis set of phases, we may have several 100,000 triplets and quartets combined. And with several 100,000 triplets and quartets, there are several 100,000 identities which must of necessity be satisfied. So that formulation of the minimal principle, I think, is a very plausible one. However, it's difficult to see how with that formulation one can ever be led to a practical scheme for estimating the values of the structure invariants, because it's a very difficult thing to force several 100,000 identities to hold. So we reject this formulation of the minimal principle and accept this one. This is exactly the same as this, but R of phi is now regarded as a function of individual phases. We imagine that these structure invariants are replaced by their expressions in terms of individual phases. So we have here a function of phases. That's a function of a small number of variables, only 200 or 300 phases or so, rather than 100,000 or 200,000 structure invariants. We have only 200 or 300 phases. And now the minimal principle assumes the following form. Those phases are correct, which minimize this function as a function of phases. And that is simply what the minimal principle is. Now, Let me see. Right-hand side, left-hand side. Okay. I have 1 minute. Okay. Well, this is simply another statement. The function of phases R of phi is a minimum when the phases take on their true values, provided, of course, which I haven't emphasized before, that the basis set of phases is sufficiently large. I want to describe in the remaining minute that I have what the application has been to cytochrome C550, which is a macromolecule consisting of some, it crystallizes in the orthorhombic space group. There are some 4,000 non-hydrogen atoms in the unit cell. The basis set of phases is 300 in number. 2,700 triplets can be generated. 244,000 negative quartets, of which we've used only 157,000, simply to save on computing time. Here we have the value of this function. I've called it R min, but the correct, it should be really R true, the true value of the function, which corresponds to the true values of the phases. Turns out to be 0.495. For 100 sets of phases chosen at random, the value of the function ranges between 0.50 and 0.517. For 5,000 randomly chosen sets of phases, we find the values are in the same range. So clearly, this example shows that even for a macromolecule with 300 phases in the basis set, the value of the function is indeed a minimum when the phases take on their true values. Now I have just one more slide. I think only one more slide. We have found the global minimum of this function. It turns out to be, this is the value of the global minimum. I won't have time to describe how we found it in this case, but it does take advantage of the fact that this is a known structure. The value of the global minimum is 0.459. At that point, in this space of 300 variables, the phases which give rise to this global minimum deviate from the true phases by 12 degrees. So we see that this minimal principle does in fact serve to define the true values of the phases. Well, this finishes my talk, except that I want to acknowledge the assistance of D. Vel-Murugan and Han-Fu San, who have done all the programming and all the calculations which were needed for this report. Thank you.